So in this lecture we are going to discuss about pullback of differential forms. In the last lecture we discussed about the push forward vectors, and we said that let's say you have these vectors v1, v2, v3 on some manifold M, and you are inducing some coordinate change function or a coordinate transformation that induces a tangent mapping or a mapping on the tangent bundle that takes vector v1, v2, v3 as t1, tv1, tv2 and tv3, where t itself was the Jacobian. Okay, and now what we ask is something like this. Let's say you have some differential n form or a n form on manifold n omega, which eats up the vectors on this manifold. That means these vectors denoted with tv1, let's call this as, let's say, v1 prime. So it will eat these vectors up and produce a real number, and we ask that can we do something like this, is that let's say these v1 primes are pushed forward vectors of this v1, v2, v3 that is situated on the tangent bundle of M, and we say that can we define some omega prime. So this is the question that we are asking. Can we define a omega prime such that it will produce the same it will produce the same number? Doesn't have to be real necessarily, but since we are dealing with only functions of real variables or manifolds where the points only give you a real number, so that's why we're calling it a real number, but it can be complex as well if you are dealing with a complex manifold and stuff. So this is the question that we are asking, that you have some form omega on the manifold n which eats vector from the tangent spaces of n, produces a number, and if you consider the vectors of n to be the pushed forward versions of some vector that were in the tangent bundle of M, can you define some omega prime that will produce the same number as well? So that's why it's called a pullback. What it's doing is that it's pulling you back from the manifold n to manifold M. Okay, so that's why it's called a pullback. Pushed forward was defined as you are pushing your vectors forward from manifold M to N, and in pullback you first do something on N, manifold N, and then you try to induce a map by pulling the form defined on N onto the manifold M. So that's why it's called a pullback. So formally we write the pullback back of a differential form as follows. T star f dot omega, this is the pullback. This whole thing is the pullback, and it's also known as the pullback of omega, this whole quantity, okay, which eats vectors of manifold M v3 vk, which is equals to omega of t of f dot v1, t of f dot v2. Again, these are the pushed forward versions of these vectors over here, this v1, v2, v3 and so on. Tf dot v3 So this is our definition of the pullback of differential forms, and now we will try to find out what this T star f is. Okay, and we will just do things in general over here. So let's consider a mapping also we are assuming that these two manifolds have the same dimension. So what happens when they are not of the same dimension, we'll get back to that through an example. But first we want to find out what is the form of this T star of f using the fact that the manifolds under consideration will have the same dimension. So let's consider a mapping. So let's consider a mapping which is denoted by phi, and the collection is denoted by the following: phi1 of x1 x2 dot dot x of n, like this, and similarly phi2 x1 x2 dot dot x of n, phi3 x1 x2 dot dot x of n, and finally phi of n x1 x2 x3 dot dot x of n, like this. Okay, and by the definition of the pullback of differential forms or pullback of forms, we see that this is a number, so this is a number, this is also a number, and this is a, let's say, differential n form. Let's say this is a n form. So oops, this should be an n. If this is a n form and this guy produces a number, that means there should be n vectors over here, right? Similarly, if there are n vectors over here, it should tell us that this is also, this pullback guy is also a n form, right? So that was pretty easy to do. Now what we will do is that we will say that we want to consider a form, a n form. So we consider a n form omega that is coming from this definition of omega as follows. And this omega is defined where? On manifold n, where this mapping takes the coordinates or the points of m and it projects those points into n. So that's why the omega form will be given by d phi 1 wedged with d phi 2 wedged with d phi of n, like this. Okay, and this you can also say that omega belongs to r of n, where this r of n is denoted with the following coordinate: phi 3 phi of n, like this. So since we want to find out what is this T star of f or T star of phi, because we are using a phi over here, so you can call it a T star of phi as well. We want to find this guy. The first thing we note that this T star f dot omega, which is given over here, and it will translate into this T star phi dot omega, this is also an n form. Why? Because we said a few minutes earlier, if omega is n form and its n vectors produces a number where on the left hand side you also have n vectors, and you want to see what kind of a form this T star f dot omega is, you can easily conclude that this is also a n form, right? Because if it's not an n form, then it won't be able to eat up n vectors and produce a number, so the equality would be violated. So you already know that this T star phi dot omega is also an n form, so we can write this T star phi dot omega as a general n form where f is a zero form. So let me emphasize that this is a zero form or a function, whatever you want to call it, because zero forms are just functions. and this is given by dx1 wedged with dx2 wedged with dx3 wedged with dot 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 dx of n, like this. Okay, so now we proceed as follows. We will consider some vectors that are the basis vectors because they're easiest to deal with. So we consider the following vectors: e1 as 1 0 0 dot 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 dot, dot up to n zeros on this column. Similarly, e2 as 0 1 0 dot 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 dot, dot. All of these are 0. So similarly, if you have a e of n, then there is only 1 at the entry point n and all the other entries are 0, like this. And we also know that this t of phi, which is just the Jacobian matrix, is given by the following. So this is phi 1 x1 phi 1 x2 dot 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 of phi 1 x of n, and this is n cross n matrix where the last entry is phi of n x of n, like this, and here it will be phi of n x of 1. Okay, now let's consider the following. Our zero form f can be written as f dx1 wedged with dx2 wedged with dx3 da 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 dx of n, and we can have the following vectors: e1 e2 e3 and so on. So what this does is that it eats out these vectors, this dx1 dx2 dx3, all of this eats out these vectors over here. This is by the definition, so that's why we consider this basis vector, so that we can use this trick over here. And note the fact that this f along with this dx1 dx2 dx3 dot 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 dx of n, this is equals to our pullback. That means this is equals to the t star phi dot omega, right, by the definition, because this pullback was also an n form, and we said that okay, let the n form take the following I don't know, phase where you have some function and then you have this wedge products. So you write this as t phi dot omega, and then you have this e1 e2 da 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 da. Now use the definition of the pullback again. That is the definition where did we give it? Yeah, this one. So let's call this the main definition as 1. So use equation 1 again, and you can write it as omega t phi dot e1 t phi dot e2 and so on, t phi dot en, right? So omega was what? Omega was a n form on the manifold where you have the coordinates as phi 1 phi 2 phi 3 and so on. So you write omega as d phi 1 as we wrote earlier. We use that now over here. So using this identity, we can write down this line: d phi 1 d phi 2 wedged with d phi 3 dot 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 wedged with d phi of n with t phi dot e1 t phi dot e2 dot 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 dot, dot t phi dot en, right? And this is what? This is just another matrix given by d phi 1 t phi dot e1, and you will have the next entries as the last entry, sorry, it will be t phi dot en. Similarly, d phi 2 t phi dot e2 dot 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 dot, dot. All the other entries t phi dot en, and so on and so forth. Now note the fact that t of phi was our Jacobian matrix, right? And all these vectors e1, e2, e3, these were the basis vectors. So if you consider any quantity that is given by, let's say, t phi dot e1, let's take this quantity first. So it has some component phi 1, x1, phi 1, x2, and so on. And if you multiply this with 1 0 0 0 0 dot 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 n, so this is the n cross n matrix. This is what, a column vector where you have n rows and one column only. It should only spit out the first component because all the other components would be 0. So this is just this guy over here, right? And similarly for the other components, you can find that this d phi 2, t phi dot en will just give you the partial derivative of phi 2 with respect to x of n, right? So finally we can write this as del phi 1 x1 del phi 1 x2 dot 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 del phi 1 x of n, and similarly all the other elements, and finally you have on the last line something like this, 1 d phi n x2 dot 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 d phi of n xn, which is nothing but the Jacobian matrix itself. So finally, and this is what, this is just the f. And notice one thing, that we use the Jacobian matrix, but using this line over here, from this line to this line, this is a determinant, right? So we were computing this f, which is a 0 form, and this is a determinant. So if you want, you can also put it on a square bracket like this, or you can put a determinant sign over here. So finally we have found f, this is equals to f, and our pullback formula becomes t star phi d phi 1 wedged with d phi 2 wedged with d phi 3 dot 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 d phi of n is just this determinant of this matrix, d phi 1 x1 d phi 2 x2 dot dot dot, like this, wedged with dx1 wedged with dx2 wedged with dx3, and so on. Or we can also write it as the very familiar formula that we see in multivariable calculus. So this is what your pullback does. So what we do in multivariable calculus is that we introduce the change of coordinates, but we never mention about the manifolds, because when you change your coordinates, you are also changing the manifold as well. We finally found the pullback, that is this t star omega, where omega is given by this d phi 1 d phi 2 dot 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 d phi of n, is just the determinant of the Jacobian, and this form itself. Okay, so if you recall the example from the last lecture where our mappings were given by phi or f, whatever you want to call it, since we are using phi over here, I'll just go with phi. Phi was given by this phi 1, which was equals to x plus y, and phi 2 equals to x minus y. Then the determinant of the Jacobian was what? The Jacobian was just 1 1 1 minus 1, and the determinant was given by 2. So if you want to consider that the area on the UV plane like this, then it would be related with the area form of the xy as minus 2 dx wedged with dy, like this, right? So when we do this kind of things, we actually calculate the pullback. That's what the pullback of differential forms tells us, that what you are doing here is that the pullback of du dv is just this whole thing. So if this is the initial omega, that means the initial form on the manifold n or the second manifold, then the pullback of this du dv would be minus 2 dx wedged with dy. And in fact, this type of pullback can also be defined for mapping such that r of m to some r of n, where m and n are not equal as well. Maybe we'll get back to that later, but this will be it for today, and I'll see you guys on the next lecture. Thank you.